This is precalc 1.2. This is on analyzing graphs and functions and relations. So the first thing you should understand here is that a graph of a function, we call it f if you want, is just a set of ordered pairs. That makes sense. Okay, a graph is just a bunch of points connected together, right? But what it is that it fulfills the ordered pair that when you put x in, you get a y out. And remember, the y in function notation is f of x. So it's x, comma, f of x. There's a direct correlation between the inputs and the outputs. That's the rule. And that x itself is on the domain of t. Or not t, sorry, it's f. So it's on the domain of f, which means the function only exists where you're allowed to put an x. If I'm not allowed to use -2 in the function, the domain does not include -2 or 2 or whatever value I just said, the graph won't exist there. Think of square roots. You can't put negative numbers in. The domain is only greater than or equal to 0. So -5 wouldn't even be part of the graph. You don't even see it. Okay? So what we have here to kind of introduce ourselves to all of this is the fact that an investor assessed the average daily value of the share of a certain stock over a 20-day period. The value of the stock can be approximated by that crazy equation on the domain between 0 and 20, where D represents the date of the assessment. Now this is what math does. Math takes something that's complicated, like the value of stocks every day, or throughout the day. And what we do as mathematicians, as people, we try to use some kind of mostly simplified mathematical equations to represent very complex situations. Think of all the physics stuff that you guys have ever talked about. All the science classes. We gathered all this data and we tried to create these simple mathematical equations that can either predict what happened throughout that whole entire data or into the future. And it seems like it doesn't always match up perfectly. We can get approximations because real life things are not nice and neat. They're messy. And so, this is what he did though, is that he plotted all of that, came up with this equation. And they want two parts from this. The first part, it wants you to take the graph to estimate, or use the graph to estimate the value of the stock on the 10th day. So how would I go about approximating the value of the stock on the 10th day? Should be fairly easy. All you have to do is what? Go to the graph. Go to day number 10. Day number 10. And go to the value. So running over here, it's like 31, 32. What do you guys want to go with? 31. Okay. So in part A, we say, hey, it's 31. That was using the graph to approximate. The second part to that question says, confirm your estimate algebraically. How can I confirm it algebraically? Oh, I have an equation that allows me to replace D with the number of days, and I'm saying there should be 10 days gone by. Can you confirm that it actually equals 31? So, basically, can you take 10 and plug it into the equation? that equal 31? So, does it equal 31? Question mark. So, I would expect you to take your calculator and start doing that. Hopefully save some people some time right now. Does anybody recognize this particular situation? Because it's not going to happen every time. Look at that first number, 0.002, and then parentheses 10 to the 4th power. Doesn't that thing itself, right here, look like something you've seen before? Some kind of notation-ish?
Scientific notation?
Scientific notation, guys. When I multiply by powers of 10, I can take the decimal and move it, in this case, to the right 4 times. So I get 20 minus 110 plus 177 minus 86 plus 31. Does that equal 31? 31 equals 32. We actually were off. Is that okay, though? Yeah, that's for approximation, so therefore we tried to confirm it algebraically. We did not confirm it, but we found the actual value at day 10. Not too bad, right? The next part wants us to use the graph to estimate the days during which the stock was valued at $30 per share, and then confirm that algebraically. So what does it mean that the stock has a $30 value? What is $30? A share. But, right. Is it the V of D or D?
Oh,
It'd be V or V of D or Y value. The output has to be 30. So, okay, after having some technical difficulties here, now we're back. And what we're going to do is we are going to estimate where our values are hitting that $30 mark. And so if I'm looking at the graph, I think what we can do is say that it looks like it's at 0, it's at 9, and it's at, let's say, 15. So I would be like, okay, 0, 9, 15, if I was using the graph to estimate where those values are. But to do this, confirm it algebraically, without having to go through all the hoopla here, I would then take 0, and I would just plug it into our equation. And it should give us the value of 31. Or 30, sorry. My bad. So it should give us a value of 30. Now, if you do this, I do not believe if I put 0 in, I'll get 30, because the equation itself says that if I put 0 in, it'll be 0, 0, 0, 0, it'd be 31. So 0 is not actually one of the zeros, but 9 and 15 probably are pretty close. But that's how I can verify or confirm it algebraically, is by plugging them back in to make sure I get those values. The other idea is that I could technically set our equation here equal to 30, bring the 30 to the other side, and then when I graph that, I can look for its x-intercepts, which will be at those same places, 0, 9, 15. The other option is to graph it just like we have here. So y equals 30 and y equals the 0.00 d to the 4th, and then use the intersect function to find out where the 3 spots are. So there's a couple different approaches that you can use to figure this out. Now the next part is to use a graph to find the domain and range. Now I like to use graphs to find domain and range because I find it to be just that much easier. First of all, if I'm given a graph, I can visually see where things possibly max out, bottom out at a minimum, where they stop and start. Because if I'm given just a function, I have to know some things about those functions. I need to know, limitations on fractions. I can't divide by 0. Square root graphs. I can't divide or take a square root of a negative number, so it has to be greater than or equal to 0. Then all of a sudden we start to put those together like we did in our homework the last couple nights. Then now all of a sudden we're restricting even more. But if I'm given a graph, I can see that my domain, which are my x values, start at -2 and go all the way to 6. So if I wanted my domain, I can say it's -2, comma 6, so interval notation, where -2 is included, but 6 is not because of the open circle. Likewise, the range, now I always start from the smallest number to the largest number. 0 would be the smallest y value that I'm allowed to be, and I go all the way up to here, which I'm going to call as like 4. 4 looks like it's included. 0 is actually included as well because of this point. That point's included even though it's open over here. I can actually get to 0 on the left side. So there's my domain and range. On this graph over here, which is more of your piecewise looking graphs, it's multiple parts of functions put together. The domain, it looks like I have to have 2 different intervals. An interval for this top section and then an interval for this bottom section. So when I do this, I can see that -4 to 2 is one of my intervals, and none of those are included at the ends because they're both open circles. I then go from the graph there and I jump down to here to another interval, which happens to start at 2 and goes all the way to positive infinity. Can't be at positive infinity, but I also cannot be at 2 again because it's an open dot. I need to put these two together, so when I marry them together, I use a union between the two. The range, on the other hand, again, I look at the smallest y value possible, and I see that the graph has been falling to infinity. So it's going to start at negative infinity and work my way up to -2. And I cannot be at either one of those. And then that's the union between all the way up to here, which is 6. Now this one's tricky because 6 is not included at the ends, but there are x values like -2 that when I plug in gives me a value of 6, so I'm actually able to be there even though I'm not there all the time. 6 would actually be a value as an outcome. The next thing is looking at graphs and determining the x and y intercepts. Now remember, x and y intercepts are where the graphs intersect the x or y axis. And so remember, x-intercepts are where the graph crosses the x-axis and the y is equal to 0, and the y-intercept is where the x is equal to 0 and it crosses the y-axis. And remember that if a function has more than one, or can't say have more than one y-intercept, because therefore the 2 points would be above each other and it would not pass the vertical line test, not a function. But you can have multiple, when I say multiple x-intercepts, you can have as many as you want, or according to the equation. Hence, sine of x or sine theta. There's many times where that sine curve, actually an infinite amount of times, that it will cross the x-axis. So make sure that you guys can do this, as in find the y-intercepts. So if I'm looking at the graph, the y-intercept looks like it crosses at 4. I'm going to call that 0, 4, because if it's a y-intercept, I want to use it as a point. Now, we probably should possibly take a look at it. How do I do this algebraically? And if that's the case, remember, for y-intercepts, I am going to plug in x equals 0. So when I do that, I get 0, 0, 0, and that's plus 4. So therefore, the y-intercept is at 4, or 0, 4. Same thing here. If I'm looking at this graph, it looks like it's just under 3, above 2, maybe something like 2.25. To figure this out, I can plug 0 in, and 0 squared plus 6 is still 6, so that's the square root of 6, and the square root of 6 I do believe is like 2.4 something. So that's how we could find that. So it would be 0 square root 6 to be exact. Zeros or roots. We would also call those the x-intercepts. So the x-intercepts of a graph are the roots, the zeros, and where that crosses the x-axis. So we can approximate the zeros by looking at the graph, and I would say we have one of them at 0, another one at 2, almost guaranteed, and then there's one between 1 and 2, maybe something like 1.3. And so we can find this algebraically because remember, finding x-intercepts, you plug a 0 in for y and solve. So 0 equals 3x cubed minus 10x squared plus 8x. And if I factor this, I can take an x out. So 3x squared minus 10x plus 8. And then you have to keep on factoring this. And if I factor this, I get 3 times 8, which is 24. And now I've got to find the factors of 24. That'll give me a negative 10. Happens to be a 6 and a 4. They both have to be negative. So 3x squared minus 6x minus 4x plus 8. And if I split up negative 10, I can use factor by grouping. And if I use factor by grouping, I can take a 3x out of the first group, it would be x minus 2, and take a negative 4 out of the second group, it would be x minus 2 again, leaving you with x minus 2, squishing together the outside parts. 3x minus 4. Don't forget that you have to drop down this first x. Everything is set equal to 0. So x equals 0, x equals 2, and x equals 4/3 because I subtract 4, divide by 3. And 4/3 is 1.3 repeat, so which is really close to what I thought it would be at 1.3. We can do the same thing on the second graph here, and I can say, hey, it looks like it's about a negative 1/4. So negative 1/4 comma 0 is where I'm saying is the 0 or the x-intercept of that graph is. I can solve it by 0 equals the square root of 4t plus 1. 0 equals, when I square both sides, subtract 1, divide by 4. T equals negative 1/4. And so one I am approximating using a graph, the other one I am finding the exact value using algebra. Line symmetry. Line symmetry is when a graph can be folded in half and it results in a mirror image. So this would be a line symmetry. Happens to be the x-axis. This one is a line symmetry. That is the y-axis. Point symmetry. Point symmetry is when a graph can be rotated 180 degrees and the graph is still there. So this point, which we'll call here, can be rotated 180 degrees and boom, there it is. And it's still on the graph. So I got 3 different types of symmetry here shown. The first one is symmetry about the x-axis, symmetry about the y-axis, and symmetry about the origin. Now, for symmetry about the x-axis, just basically says that if I take a y and replace it with a negative y, I will end up with the same equation. Same thing with the y-axis. If I can take x, replace with a negative x, and it produces the equivalent equation, it's about the y-axis, symmetric, and the origin would be both the x and with a negative x and y with negative x, y, and it results in the original equation. So let's put this to use. So when I do this, all you have to do is tell me on these graphs what kind of lines of symmetry are there. And if I look here, I can see that there's a line of symmetry of the y-axis because if I put in x, say at 1, I get 1. If I put negative 1 in, I also get 1. That is symmetric about the y-axis. Going over here, I can fold it in half above the x-axis, the y-axis, and the fact that if I take this point, I could flip it about the x, flip it about the y, and there it is. So therefore, it's also symmetric about the origin. The last part is that these things that are symmetric about the x and y axis, or symmetry, have special names. They're even functions and they're odd functions. And like it says here, that if I can take a negative x value, plug it into a function, and I get the original function back, we're going to call that even. But if I take a negative x value, plug it into the function, and the negative actually comes out front of the original function, that is an odd function. And so each one of these kind of highlights a different thing. I got one that is odd, one that's even, and one that is neither. And so the first one here is if I take and put a negative x in, I'll have 2 over the opposite of x squared. But when I square negative, it becomes positive. And if this is the original function, which is f of x, therefore this is an even function because the function evaluated for negative x is the same thing as f of x. Think of your quadratics, parabolas, things like that, where you square it and the negative disappears. That's an even. The middle function, which if I wanted to put in a negative x value for, would become 4 square root of negative x. Now, hey, wait a minute, we don't like or can't take the square root of a negative number, so therefore it's not on the domain, therefore it is neither. Next one, put in a negative x, and when I do this, I get negative x to the 5th minus 2 times negative x to the 3rd plus a negative x. Now remember, when you take an odd power of a negative, it stays negative. So this would be a negative x to the 5th plus 2x to the 3rd, because the negative of x, negative x to the 3rd power, will counteract with the negative in front, and minus x. Now hopefully you recognize that the original problem has a positive x to the 5th. This one has a negative x to the 5th. So it's really easy to factor out a negative, or just a negative 1, which means I just change all the signs here. And you should recognize that that is negative of h of x, which means it is odd. So if you use the process and you do this right, you will be just fine. Your homework is page 19, 1 through 40, every 3. Have a great day.